we are very close to being able to look at some variable temperature NMR spectroscopy, which can be quite exciting puzzles. So the last NMR spectrum we predicted was this fluorine-19 with the deuterium. And just for fun, let's actually also include that boron-11. Right? If boron-11 has a spin of 3/2, deuterium has a spin of 1, and fluorine has a spin of 1/2, what would your predicted fluorine NMR look like? So we still just have two signals, so we have a single signal. And it's going to be split by boron first, because it's closer and it's also larger than deuterium. And so it's a single boron nucleus, so 2Ni plus 1 is the multiplicity. So we will have 2 times one other nucleus, and the spin is 3/2 plus 1, so this cancels. 3 plus 1 equals 4. So that's going to split into a quartet. All right, 1, 2, 3, 4, all one large signal. And then each of those is going to get split into a triplet. So we're going to have a quartet of triplets, all right? But those triplets are going to be of equal height because it's a single nucleus. If it was proton, it would be a doublet, right? So we would see a quartet of doublets where the doublet has equal height. And so here we see a quartet of triplets, and those triplets are equal height. So it's important that they don't look like normal triplets, because that's not what they are. Anyway, that's just for fun. And so the last one before we tackle the variable temperature stuff is a phosphorus NMR of this phosphite, or whatever, it doesn't matter. Single phosphorus, single signal, but we have coupling to hydrogen as well as fluorine because they're not decoupled. So of course I tell you the strength of the coupling constants. I say that the hydrogen coupling is stronger than the fluorine coupling, phosphorus hydrogen coupling, which is of course ludicrous, but let's just go with it because the professor said so, right? Why is it ludicrous? Because fluorine is a much larger nucleus. It's going to be most likely the stronger coupling. But either way, we are going to split the signal by one hydrogen. There's one other nucleus into a doublet. So again, what I do is I make that first stronger, splitting the larger, so that I can then further split each of these lines into something else, right? So then we have two fluorine nuclei, spin 1/2, so it's going to split each one of these lines into a triplet. So it's going to be a doublet of triplet. Fair enough. All right, so here's another one, and it's more complicated, and I will actually accept multiple answers as long as they make sense. For example, first of all, it's proton decoupled, so we don't have to worry about any of these protons here, right? So no worries. So it's all about fluorine. And the part that you should for sure get right is the assignment here. So we have these fluorines. It's a flat molecule, but as I indicate, these obviously it's a tetrahedral carbon, so those two fluorines are going to go into the board and into my face, so they are chemically equivalent. There is the equivalent. There's a mirror plane in the plane of the board. And then these two are also different. So we have B and C. These are not equivalent. That's not really a mirror plane through here. So they are different. So we have three signals, A, B, and C. And then you might come up with different kinds of answers. Okay. So B and C split each other into doublets. And that should be the same coupling constant. So that's going to be large coupling. And since I do say long-range coupling, I am implying that these are also going to be split by those two. So B is going to be split into a doublet, and C is going to be split into a doublet, and that coupling constant, that distance between these two peaks, should be equal to each other because it's the same coupling constant between those two fluorines. Now, if long-range coupling exists, that means that C and B are both also split by two other fluorines, but it's going to be a much weaker splitting pattern because they are further away. So all that means is that each of these signals gets split by two other nuclei into triplets. So we get two doublets of triplets for B and C. Now first of all, A doesn't split itself. Once again, they're chemically equivalent. They don't split each other. It's just a single signal. But they will be split into a doublet of doublets. And so just so you can see the difference, that the splitting would probably not be this far apart, but just because they are. And so we do have 1, 2, 3, and 1, 2, 3, 4. So 3 and 4. So it's quite possible that coupling to C is just a little bit stronger than B. It's also possible. Think about what happens if this gets smaller and smaller, right? If this coupling here is really not as amplified or much larger than the other one, so we get them, they get closer and closer, and then sometimes when they're almost equivalent, these two will grow into each other, and then they appear to be a triplet, right? If the coupling constant, and so that's also entirely possible. But you should recognize that there should be two different nuclei. They're not chemically equivalent, and so the signal for A should be a doublet of doublets. Anyway, moving on to the good stuff. So this is the variable temperature NMR of SF4 that I showed you, and we didn't discuss much, but what you want to do is you want to draw a reasonable structure that is expected, where I provide you with a structure. And based on that, this is a seesaw. We have two different signals. So maybe just completely ignore everything and draw a structure or predict a spectrum based on the structure that I provide. See what you expect to see. So we have two different signals, and so these should be two triplets, because we have A and B, so each of these is split by two other nuclei into a triplet. And sure enough, that's what we see here. So at low temperature, we see this frozen out. So you basically have 80% of the problem solved yet. Now you just need to come up with a mechanism or a proposal of how these A's and B's are possibly going to exchange. Now, don't you dare call that a Berry pseudo-rotation, because it's not a trigonal bipyramid. To call it, don't give it a name, just explain it or draw it out. So it's pretty simple to fathom that there's vibration here, and that these two groups can move up into a square planar geometry. So we can actually see these groups grow here, right? The lone pair can be squeezed. And so now we have, and I'm going to just go A and B. So this is a seesaw, and this is square planar. And perhaps I should redraw that real quick. I probably should have just drawn that in ChemDraw, but here it is anyway. So you should clearly show the seesaw and square planar and label the geometries and have equilibrium arrows between them, so to indicate the dynamic process that might be occurring here. We have an exchange of these positions. Simply, that should be a pretty low energy barrier of these to go up, and then these to go down to go back to a seesaw. So we have a seesaw square planar geometry exchange, and that's all that is. That's not called Berry pseudo-rotation, but that clearly would explain why we see one signal. And so you want to explain that at room temperature there's an exchange between the two inequivalent fluorine positions, and there most likely is a square planar to seesaw geometry interconversion, and that causes that the NMR time scale to not be able to detect at room temperature because the speed of this dynamic process is faster than the NMR timescale. But as you cool this down to negative 98 degrees, you are able to freeze out that motion and detect the expected two triplets for the two different fluorine environments of SF4, which is a seesaw. And that's simply what we would expect. And then you are done, 10 out of 10, moving on. So here's another example. This time it's a fluorine NMR spectrum of PF3Cl2, right? So that you can call Berry pseudo-rotation. And so the first thing I would do, as always, I would draw the different geometries that you might expect, right? So we have a trigonal bipyramid. We would maybe put the chlorine atoms in the equatorial positions here because they're larger, there's more space as we've discussed, and then have fluorine and fluorine here. So that's one of the possibilities. But there are two other isomers that you can draw, and you know, one of them will have the two chlorines here, and you can consider all of those. You know, that right there would be a single signal, right? So for fluorine NMR, all of those would be chemically equivalent, and then they would be split by phosphorus into a doublet, right? So that could be that, but we know that's not it because that is the high temperature, not minus 22 Celsius, still higher than minus 143. So there is a dynamic process here, and so the other isomer that we have also has three signals, right? So this would be A and B, and then if we had a chlorine, fluorine, and fluorine, we would also have here, let's say A and B, and both of those possibilities. And again, the most likely one is going to be this one because the chlorine atoms are going to be more likely to be in the equatorial position. Either way, the spectrum you come up with are two signals where, first of all, phosphorus is closer and more powerful nucleus. It's going to have a larger splitting pattern. It would split signal A into a doublet, and it would split signal B into a doublet, right? And if you look at the distance between these two signals here, it's the exact same distance. So that is your fluorine to phosphorus coupling for sure. All right. So each of these fluorines gets split into a doublet, and then A here gets split into a doublet of doublets. So this would be A, and B gets split into by two other nuclides into a triplet. So a triplet of doublets. So once you've figured that out, you can just explain, label the spectrum, draw a structure, label all of the atoms, and explain why it is a doublet of doublets and a doublet of triplets. You can even go into more detail and talk about the size of the splitting. And also this splitting here is the same because that is the fluorine coupling, right? There's a whole lot you can elaborate. And then that is Berry pseudo-rotation, or if you don't know what that buzzword is, which I don't care, I want you to describe or draw the exchange between equatorial and axial positions due to movement of these positions into a square pyramidal geometry and then back to a trigonal bipyramid, and that's how they exchange. So that's another example of what we might expect. And here you go. That's your mechanism here. It's Berry pseudo-rotation. And so really not a big deal. Here's another spectrum here. So this is a phosphorus 31 spectrum. And it's square planar. Rhodium-1, that's a D8 complex. And this is what you would expect, right? Okay, so this is not dynamic, first of all, but we need it in order to answer the next question. And so what we have is we have two signals here. Let's call this A and B. And so B gets split into a triplet, and A gets split into a doublet. So where is this coming from? Two other possibilities, either rhodium or chlorine. It's a rather large splitting pattern here, right? This distance is rather large, so it's most likely rhodium. So rhodium must have a spin of 1/2, which will cause each of these phosphorus environments to be split into a doublet here. So this is the rhodium to phosphorus coupling, and so we get a doublet of triplets. So this would be signal B here, because that's split by 2 phosphorus environments, and this would be phosphorus A. Okay. With that in mind, let's take a look at this variable temperature NMR series here. Now this is the active catalyst, so when the chloroligand leaves, it becomes an active catalyst for hydrogenation. But that's a story for another lecture. But if I gave you these two spectrum, let's say this is low temperature and this is high, and I give you this structure, what you might come up with is you have 3 groups, so you might expect them to be trigonal planar, where all groups would be equivalent. So that's a reasonable assumption, and so we would only see a single phosphorus signal, and it would be split by rhodium. But we do see this at high temperature, and at low temperature we see 2 different signals, okay, right? Because this is one phosphorus environment and this is another. So somehow there has to be a way for these phosphine groups to do some sort of motion, and so the only reason, or there might be anything reasonable you come up with is fine. But if you simply put this geometry into T-shaped, we now have two different signals here. Just like we did for the cis, it would have the exact same. If you knock this off and it stays as a T-shape, you would have the exact same splitting pattern, and that's what we see here, right? The triplet of triplets from PB here. This would be B, and this would be A. So it would be pretty simple to come up with a mechanism that just shows an exchange, and this just, both of them are T. You might want to show the trigonal planar shape in the middle as an intermediate, as a third one, but that would be a reasonable explanation for the low temperature spectrum. And it actually turns out to be true. They did some studies that this is the active catalyst will have a T-shaped geometry. Alright, so the next one is pretty interesting. It's called ring whizzing. It involves an eta-1 cyclopentadienyl group here. And so before we look at this, it helps to do an electron count on this titanium complex here. So titanium has 4, then these 2 eta-5 groups each have 5. So the eta-5s, of which we have 2, is 10. And the way these are shown as eta-1, so we have 2 times eta-1, that would be 2 electrons. So this is a 16 electron species. So it makes sense that it would try to gain, it could try to go eta-2, but it doesn't do this. It can't do this very comfortably, or it can switch to eta-5, and that's then too many electrons. And if we look at this spectrum here, it's actually not quite frozen out entirely, because if you think about it, if this was frozen out, we still have a hydrogen here, and here, and here, and here, and here. And so we would, and I'm going to write over this would be A, this would be B, and this would be C. So we actually expect 3 different signals. We don't see that at the low temperature. So there may still be some sort of dynamic process happening that makes A, B, and C chemically equivalent at negative 27. But there's something else that's going on here, because the eta-5 and the eta-1 cyclopentadienyl protons are all equivalent at high temperature, so every single one. So there must also be some sort of exchange between eta-1 and eta-5. So imagine, and you can just put this into words, you don't have to really write that because it's kind of tricky to do. So there has to be an exchange, you can just say between the eta1 and eta5. So this eta1 will go into eta5, which of course puts 20 electrons onto this titanium, which it can't handle, so it has to push this one out to eta1. So there's that eta5 to eta1 exchange, but there has also got to be something that makes all of these hydrogens complete or equivalent, and that is referred to as ring whizzing. So this actually rotates this in this fashion, right? So this rotates around very fast, where, you know, B flips into A, and A flips into B, and this B flips into C. So they go around like that, and that's faster than the NMR time scale here at negative 27 degrees. So this is called ring whizzing. See here it's attached to the metal, and so here I have hydrogen just exchanging, and so that still is occurring at negative 27. So we did not freeze that out. However, you can freeze that out for some spectra, and so this is a really good example here. The CP, I'll give you the formula. You can draw the structure. So if you put iron, and then you have, this is getting pretty ugly. So we would have would have 8 and then 10. That's already 18. So that's not going to be feasible. So one of those may be eta5. Plus we have the 2 carbonyls. So if we do that first, we do 8 plus the 2 carbonyls, which is 4. We get 12. We need 6 more. Okay, so that's perfect, right? Because we can do 1 eta5. That would be and 1 eta1, and so we would have an 18 electron species. This is a proton NMR, so we expect the cyclopentadiene that's eta5 to be a singlet, and if you do integrate that, it should have an integration of 5 representing 5 protons, and that shift doesn't move and it just stays the same, and so that is that group here. And then we have 3 more signals or 2 more signals, and so if you integrated that, it would be like 1 and 4. So we don't quite have the 3 signals that you expect. I'm just going to call this A and B. So we have B, and then we have C. And so this pattern here is called pseudo triplets, and they are fairly representative of that eta1 cyclopentadienyl group that is attached here to the iron. And so this represents this hydrogen here, A, and then we have C and B in this multiplet, and that's good enough. So that's somewhat frozen out. So here at somewhere between negative 80 and negative 100, you have that ring whizzing frozen out. Now if you recall, the other titanoxene complex was just at negative 27. So if you lower your temperature, and sometimes it depends on your solvent, right? If your solvent freezes out, so you can't go into lower temperature. If you use chloromethane, you cannot go to negative 100. You kind of have a limit, so you have to use like toluene, and it's also true for high temperature. But anyway, this is the end of my examples. Hopefully you have a good understanding of basic NMR, and will be able to solve any wacko dynamic process I send you away.